Good morning. Happy Thursday. So today we are going to move on to section 3.1 and probably get into 3.2 also. That's kind of the goal. That means by next week, early next week, we'll be through the first three sections, which is on that next homework. We'll see how far we get today. I'll probably end up pushing the homework back even one more day. Right now I've got it on Monday. It'll probably be Tuesday. But just keep in mind you've at least got the weekend to get a start on that one, because we'll get through at least the first couple of sections of what's on there probably. Okay. The other things that are due this week, though, don't forget the 2.8 homework, if you haven't finished it already, is due by midnight tonight. And then the test, sometime today or tomorrow, you need to carve out some time to take the test because that was posted last night and it will be due by midnight tomorrow night, Friday night. Okay. So those are the two things to get done before the weekend. And then if you want to get started on the 3.1 to 3.3 homework, we should get through a good chunk of that information today, so that you can get a start on that over the weekend. Okay. Any questions, comments, concerns about stuff that's coming up right now? All right, and the other thing I wanted to remind you of, just on the test, right, please make sure that at the end of your test that you actually hold up your papers to the camera. That's a way for me to verify that nothing was changed, just in case you run into issues with scanning and uploading. The other thing is, if you do run into those issues, please just take some pictures of your test and just email them to me, just so I have it within that 15-minute window. That way, I can verify that hopefully nothing was changed. But if you're waiting 30 minutes, because your scanner's broken or you can't get something to upload correctly or whatever, please make sure you take those pictures and just email them to me within those 15 minutes. Okay. All right. So 3.1, we're going to look at max and min values in this section. Okay. So this is something you covered back in Math 171 pre-cal. We're going to look at kind of the same things we looked at back then, but then how we can use calculus now to help us define these min and max values. All right, so first off, an extreme value, we're going to let c be some real number in the domain of our function. F of c then is what we call an absolute maximum or a global maximum value of that function on its domain if f of c is greater than or equal to f of x for all the x values in the domain. Okay, so basically, if it is the highest possible y value on the entire function, then we call it an absolute maximum. That's what that tells us. And on the other end, if we have an absolute or global minimum value of our function on its domain, then our f of c value is going to be less than or equal to the f of x for all the x in the domain. In other words, it's the smallest possible y value of all the y values in that function. Okay, so absolute max, biggest y value, absolute min, smallest y value. And that's in the entire domain of your function now. We also have what are called local extrema. Okay, so the number f of c is going to be a local maximum value if f of c is greater than or equal to f of x when x is near c. Okay, and that's kind of ambiguous to say it's near c. We're basically just looking from the left and the right now. If there happens to be a turning point in your graph, and that is the highest y value around that turning point, then we say that it's the local maximum. And then the same thing on the other end, we have a local minimum value if that f of c, that y value, is less than or equal to f of x when we're close to that c value. Okay, so from the left and the right, if that f of c is the lowest possible y value, then we call it a local minimum. All right, so absolute, min, and max, those are the absolute highest and lowest y values for the entire function on its domain, whereas local min and max values are just near that value, wherever we have turning points now. Okay, so here's a picture to kind of illustrate what we were just talking about. So notice here on that first interval around 4, we have a local minimum, right? We have that turning point there. It's not the absolute lowest point on the graph of this function, though, right? So that's why we can only call it a local minimum in this case. Same thing in that interval around 8, we have a local maximum. Again, it's not the absolute highest point, because the absolute highest point would be somewhere over here. Okay, so the local maximum, we have a turning point there, and that's a local max. Now, this one down here in the k interval around 12, This point's actually going to be what we call a local and an absolute minimum, okay, because on that domain now, it's the absolute lowest point, and it's also a turning point of your graph. Okay, so we can call that both a local and an absolute minimum. Okay. In general, only turning points can be local. If we have endpoints, and we'll look at this on one of our examples, those could be absolutes, but they can't be locals, right? So like if I was saying that this is my defined domain from this point to this point, those endpoints could be an absolute max or min. So we could actually call this point up here an absolute maximum on that domain because it's the absolute highest point, but it's not a local maximum because there's no turning point there, okay? That's the key difference between absolute and local. Locals have to be turning points. Any questions on those definitions now? All right, so let's take a look at this one. We want to find the local and absolute max and min values of our function cosine x. All right, so all we're going to do here is we're going to think about the graph of these functions for these first few examples, and then think about where we have min and max values. So what do we know about the cosine function if we were to sketch this graph? All right, so good. So we know it's going to bounce between -1 and +1 on the y, right? So I can go ahead and put those values on my y-axis. I have -1, +1. All right. What else do we know about the cosine function? All right, it's periodic, right? And the period is going to be 2 pi. Where does the graph start then if we want to graph one full period of cosine? Okay, good. 0, 1. So this point right up here is going to be our starting point. And like you said, the period is going to be 2 pi. So what's the value going to be at 2 pi then? 1 also, right? So it starts at 1. And once we get to 2 pi, we should end up at 1 also. All right, now we just need to fill in some points in between and sketch this. So the halfway point now between 0 and 2 pi, this is going to be pi. What would be the y value at pi? It's going to be -1. Good. So that's where it hits that lowest point right here. And then we have these intermediate points here. So this is going to be pi over 2, 3 pi over 2. And so what's the value going to be at those 2 points? 0, right? So that's where we cross the x-axis. Those are our x-intercepts. So if I graph one full period of cosine, it's going to look something like this. All right, and again, it is periodic, right? So it's just going to repeat that pattern over and over and over again. All right, so now let's talk about our local and absolute max and min values. Okay, now this is key because whenever you see the word values here, this means we're looking for the y's. Okay, we don't really care about the x's. Sometimes you'll need the x to be able to figure out the y, but whenever it asks for a max or min value, it's asking specifically for the y value. So, do we have a local min value this time? Yes, right? What's our local minimum value? It's going to be at pi, and the value itself is going to be -1, right? So it happens at x equals pi. The value is y equals -1. Okay, so this point down here now, we can call this a local min. All right, do we have a local max value? Yeah, right. So what would our local maximum value be? Okay, good. So you could choose either one of those points, right? So we can just say this is either at x equals 0 or x equals 2 pi, but the value itself is going to be y equals 1, because remember, this is going to continue, right? So that's not the end of your graph. So those are turning points still. So we still have a local maximum value of y equals 1. All right, now, do we have an absolute min value? Okay. So is there anywhere where we have the absolute highest y value? Or sorry, lowest in this case. We're looking at minimum. So absolute minimum value. -1, right? Okay, so -1 is still the absolute lowest y value that this function hits. And so we could say again, it happens at x equals pi, but the value itself is still y equals -1. So -1 is both a local min value and an absolute minimum value. All right, and then what about an absolute max value? It's going to be 1, right? So again, that's the absolute highest y value that our function hits. And so again, we can say that it occurs at x equals 0 if we want to, but the value itself is y equals 1. Now, technically in this case, how many times are you going to hit each of those max and min values? Every 2 pi, right? So it's going to be an infinite number of times that we hit that. So we're going to say this could be plus 2 pi k, plus 2 pi k, plus 2 pi k, just in case you want to know where this actually occurs, right? It's actually those maximum values will occur every 2 pi. But again, if in the homework you're just asked to find the min and max value, all it's asking for there is just those y values. So this would be the local min, this would be the local max value, this would be the absolute minimum value, and this would be the absolute maximum value. Any questions on that one now? And remember, you have access to Desmos, right? So feel free to use that to graph these functions. Okay, if you're struggling with actually remembering what some of the graphs look like, or you just need some assistance finding those, highest and lowest points. We will look at some functions where, it's not a familiar one. We'll need to use Desmos anyway, right? But feel free to use Desmos whenever you need to help you find those local mins and maxes. All right. Now we want to find local and absolute max and min values of x squared. So again, familiar function, right? What is this function going to look like if we graph it? Okay, all right, so we have a parabola this time, a U-shaped graph. Vertex is going to be at the origin. In which direction is it going to open? It's going to open up, right? So it's positive x squared, it's going to open up. Vertex is going to be here at the origin. So we get a parabola that looks something like this. Okay, and it doesn't have to be perfect, right? Okay, because all we're looking for here are the absolute and local min and max values. All right, so let's just go through our list here. Think about what we've got. So I'm going to start here with a local minimum value. Do we have a local min value this time? 0, right? Okay, so in this case, there is a turning point at the origin. That is a local minimum value. So that occurs at x equals 0, but the value itself is y equals 0. All right. What about a local maximum value? There isn't one, right? So in this case, that graph continues up to infinity. There are no other turning points on this graph, so we have no local max values. All right, now let's look at our absolutes. Do we have an absolute minimum value this time? Same as the local, good, right? So that's also the absolute lowest point on the domain of that function. So that's going to occur at x equals 0, and the value itself is y equals 0. Okay, so this point right here is both a local and an absolute minimum. All right, and then if we're looking for an absolute max value, do we have an absolute maximum? So we don't typically call infinity because if we're looking for values, they need to be numerical, and infinity is technically not a number, right? So in this case, we would have to say the same thing we did for local max. We would just say that there is no absolute maximum value this time. So yes, in terms of graphing, it's important to understand, yes, it's approaching infinity, right? Okay, but infinity is not really a number, and so we just have to say there is no absolute maximum. Any questions on that one now? And again, just for homework purposes, right, whenever you see that word value, just know that all they're looking for here are those y values. Okay, and that's all you'd have to input there. All right, let's take a look at this one now. So this time we've got x cubed, still looking for local and absolute min and max values. So first off, what is this graph going to look like? Yeah, right. So it's an S-shaped curve turned on its side. Okay, it's going to go through the origin here, and it's constantly going to be increasing from left to right. So it's going to come up like this, levels out here at the origin, and then it continues up like this. And again, if you need to use Desmos to graph it to see what it looks like, that's perfectly fine. All right, now that we have the graph, though, let's go through our list. So let's look for absolute minimum value first. So do we have any local min values? There are none, right? So in this case, there are no turning points of our graph where we would have a minimum value. So there are no local mins. All right. What about local max? Same thing, right? So there's no turning point, so there can't be any local maximum values. So again, there are none. Okay. What about absolute minimums? None, right? This thing goes all the way to negative infinity. That's not a numerical value. So we have to say there are no absolute minimum values. And then absolute max, same thing, right? So because it's going to positive infinity, there are no absolute max values this time. So whenever you have a function like this that's constantly increasing or constantly decreasing, no turning points, right, and no absolute highest or lowest point on the graph, then we just have to say, yep, there's no local or absolute extremum. Any questions on that one now? All right. So here's one that you probably don't know exactly what the graph looks like, right? So we will use Desmos to help us out on this one. But again, we're looking for local and absolute max and min values of this function. Now notice this time, we're given a set domain for our function. So we're not looking at all real numbers, even though it's a polynomial. We specifically want to focus on the domain from -1 to +4. All right, so I'm going to show you how we can actually input this into Desmos and restrict that domain here, okay, so that it only graphs what we want. All right, so we'll start by just putting in the functions. We've got y equals 3x to the 4th minus 16x cubed plus 18x squared. So obviously that's a polynomial. All real numbers is the domain. It's going to continue on forever and ever. If you want to restrict the domain, though, between -1 and 4, we're going to use curly braces to restrict that domain. And we're going to go -1 less than or equal to. So if you just do the less than and the equal to back to back, it'll automatically give you a less than or equal to sign. Then we put our x and then less than or equal to +4. Close your curly braces. Now I'm going to zoom out here so that we can actually see the entire graph. And then I'm going to adjust my x here, -10 to 10. I need to make my y value here a little bit bigger. So if you notice, I clicked on the little wrench here, and that's where I'm adjusting the values. So I'll just bump that up to 60 just so I can see the top. And you can see that it cuts it off, right? It starts here at -1 on the x, and it ends right here at 4 on the x. So that's what our graph would look like this time. All right, so first step, let's look for any local max or min values. Okay, so I'll start with local minimum. And I'm going to write this in the notes, and then I'll go back to it after we look. So are there any local min values this time? Yes, right? So where does it look like we might have one local minimum value? Okay, good. So it looks like at 0, x equals 0, there should be one. And then again, there's another local turning point down there around x equals 3. So in this case, we can just actually click on those points, and it'll give us those values. So we have a local min value at x equals 0. And that minimum value is y equals 0. And then we have another one at x equals +3. And that value is -27. So 2 local minimums this time. So we have those 2 turning points where that's the lowest point around that y value. All right, now let's look for local maximum values. So do we have a local max this time? Okay, so it looks like, okay, so Dean's saying at -1, 1, and 4. Okay, so keep in mind here, if it's a local, it has to be a turning point. Remember, we said that endpoints cannot be local extrema. So would we actually have just one, right? So that's the only place that we have that turning point where we have a highest point. So right in here now, at 1, the y value there is going to be 5. So 5 would be a local maximum value. So again, just remember, locals can only be turning points. Endpoints can only be absolutes. Okay. All right, now let's look for our absolutes. So we'll start with absolute minimum. Good, right? The absolute lowest y value on the domain of this function now is going to be at x equals 3, and that value is going to be negative 27. Okay, so that point down there is both a local minimum and the absolute minimum of this function now. Now, absolute maximum value. Okay, so be careful here. Is 5 the absolute highest y value in the domain of that function right now? It's not, right? So where do we actually see the highest possible y value on that? All the way over at -1, right? That starting point of our function now is where the highest possible y value occurs. So it's going to be all the way up here. And so if you just trace along your function, you can see the endpoints. You could also just plug in -1 into the function and get that y value. That's another way to get it. Okay, but in this case, -137 is going to be that point. So that's the endpoint there. Notice that that's higher than the other endpoint, okay, which is up here at 32. So -1 is where it occurs. 37 is the absolute max value. And so those are our local and absolute extrema now. Any questions about finding those values? All right. Like I said, let me go back to the notes now. I wrote all that down so you can see it. Okay, so our local minimum value, we had two of them, one at x equals 0 and one at x equals 3. The values themselves were 0 and -27. Then we had the one local maximum turning point at x equals 1. Y value there was 5, so that's our local maximum value. We also had an absolute min value of -27, right? Because that was the absolute lowest y value of the entire function. And then we had that absolute max that occurred at the endpoint, okay, and that was at -137. In general, if you're given a set domain like this, you're always going to have an absolute min and an absolute max, unless for some reason in that domain there's an asymptote or something and it's approaching infinity. That's the only time that that wouldn't happen. But as long as it's continuous along that entire domain, one of those endpoints is going to be the absolute min or max. Okay. Any questions on that one now? All right. Now, extreme value theorem. If f is continuous on a closed interval from a to b, then f attains an absolute max value f of x and an absolute minimum value f of d at some number c and d in that interval. And this is what I was just saying before. As long as it's continuous and it's a closed interval, then there has to be somewhere where we hit an absolute min and max value, because it could happen at the endpoints or it's going to happen somewhere in between, right? Those are our two options. Okay, but it's guaranteed to happen at least once in terms of max and min. And you can see that with these top three graphs. Okay, if we go from A to B, in this case, we have an absolute maximum value here on that interval at C, and then we have the absolute minimum value here at D. Okay, so if it's a closed interval and it's continuous, we're guaranteed to have both an absolute max and an absolute min somewhere in there. Now, next graph here, we start at A, we end at B. Notice here the absolute maximum occurs right here at C. And then the absolute minimum is the endpoint. And this is why we're guaranteed to have both, is because, you know, if it doesn't happen at some turning point along the way, it's going to happen at one of the endpoints. And again, this only tells us we're guaranteed to see at least one max and one min. It could happen multiple times. So notice here we have an absolute maximum at C1 and another absolute maximum over here because they hit the same Y value. And then our absolute minimum happens down here at D. Again, has to be a closed interval, the endpoints have to be included, and it has to be continuous. And if those two things are true, then we know that there's going to be an absolute max and an absolute min somewhere in that interval now. Now, the bottom graph shows why both of those things need to be true. Okay, so in this case, we technically have a closed interval because we're defined from 1 to 2 on that first graph. What's wrong with that graph, though? Which criteria does it not meet? It's not continuous, right? Okay, so this one right here, not continuous. And because of that, okay, we are going to have an absolute minimum value on this one, right, at the endpoint at 2, but there is no absolute maximum value, right? Because this up here is actually an open circle, and so there's no absolute max. Okay. Now, let's look at the next one. We have an open circle to start our interval. We have an asymptote to end our interval here. So what's the issue with this graph? Which criteria are we failing to meet this time? It's not a closed interval. Good, right? So this one right here, the interval's not closed because the endpoints are not included. And so we can't guarantee that we're going to have an absolute min or max. In this case, we would not have either, right? Because the left-hand endpoint can't be a local minimum because it's not actually defined. And then the other side's going up to positive infinity. So there's no absolute maximum either. All right, so a horizontal line. So let's just say we've got a line like this. Let's call it x equals some c value, right? And we're gonna let's make it closed. Sorry, I put arrows on the end. Let's just define this as a horizontal segment that goes from here to here. This is A, this is B. All right, so we have a closed interval, right, from A to B. The endpoints are included. It is a continuous function, right? The horizontal line is still continuous. What would be our absolute minimum value this time? C, right? So the absolute min value is going to be C. What's the absolute max value going to be? C again, right? Okay, so horizontal line, because it's a constant function, right? It's going to hit the same value everywhere. The absolute max and the absolute min happen to be the same thing. Okay? That is a possibility. But yes, it still would have both an absolute max and an absolute min. It just happens everywhere along that interval, and they're both the same value. Any other questions there? All right. Now, Fermat's theorem. If f has a local maximum or minimum at C, and if f prime of C exists, if it's defined, then the first derivative, f prime of C, is going to be equal to 0. Okay, now, be very careful how you interpret this. This says if those first two things are true, then that last thing is true. Okay, but both of the first two criteria have to be met first in order for that last thing to be true. So if there's a local min or max at C, and if the derivative at that point exists, then that derivative has to be equal to 0. Okay? But you got to check the first two criteria first in order for that last piece to be true. Now I'm going to show you a couple of examples of why it's important that we check it in that order and we make sure that both the first pieces are true before we assume the last piece. All right, so we want to find f prime of 0 or f of x equals x cubed. Okay, so we know how to find derivatives now, right? So if I wanted to find f prime of 0, what would I do first? Okay, good. Just use your power rule to find the derivative. So what's our derivative going to be this time? (3x squared). Good. Now, if I want to know f prime of 0, what are we going to do next? Just plug in 0 to that derivative. So f prime of 0 is going to be 3 times 0 squared, and that's going to be equal to what? 0. Now, does that mean that there's going to be a local min or max at that point? So I have my first derivative. It's equal to 0 at 0. Does that necessarily mean that there's going to be a local min or max there? Not necessarily, right? Because remember, the order here matters. If there is a local min or max and the derivative exists, then we know that the derivative is going to be equal to 0. But just saying that the derivative is equal to 0 does not guarantee that we have a local min or max. You can't read it in the other direction, right? And if you remember x cubed, we already looked at this graph. So it looks something like this. The reason the derivative is 0 at the origin is because it levels out right there, right? And so there would be a horizontal tangent line at that point, but it's not a min or max value. Okay, so just be very careful how you interpret this. Just because something f prime of whatever is equal to 0 does not necessarily mean that there's going to be a local min or max there. Okay. Any questions on that one? All right. Now we want to find the local minimum value for f of x equals absolute value of x. Okay, so let's think about this graph, right? What do we know this graph looks like? It's a V, right? Okay, so we have our point here at the origin, up and to the right that way, down to the left that way. So there's our V-shaped graph. Now, what is the local minimum of this function then? 0, right? Okay, there's a turning point there. Okay, the origin itself is where that occurs. So we do have a local min at 0, 0, right? So the min value would be 0. It occurs at x equals 0. Now, let's think about the derivative here. What would be the derivative f prime at 0? Does not exist, right? Because remember, we talked about if there's a sharp point there, and we broke this down using piecewise functions before back in chapter 2. Okay, but if you try to find the derivative of that sharp point, the limit of the slopes from the left and the limit of the slopes from the right is not the same. Therefore, that derivative at 0 does not exist. So in this case, we're saying that it's possible to actually have a local min or max and for the derivative not to exist at that point. Okay, so don't just assume that if the derivative doesn't exist, that there is no min or max. Okay. That's why Fermat's theorem is very specific in those first two things have to be true first, and if they are, then we can say that the derivative is equal to 0. Okay, but we can't say that because the derivative doesn't exist there, that there isn't a local min or max, because we've just shown that it could be, and we can't say that just because it's equal to 0, there is a local min or max, because we showed an example that says that's not true either. Okay. Any questions on this one now? All right. So what this basically tells us then is that when we find our derivative and we find the values where the derivative is equal to 0, those are what we call critical numbers. Those are places where interesting stuff is happening, but we don't necessarily know that there's a min or max yet, right? Okay, but it's basically telling us these are the places we might want to look at, do a little bit more research, and figure out if we have mins or maxes there. Okay, so basically we're going to take our derivative, we're going to set it equal to 0, and we're going to figure out where it's undefined, right? So if you have fractions, especially wherever that denominator is equal to 0, those are also critical numbers. Those are other places we want to look at to see if maybe we have anything, interesting happening there, possibly mins and max values, right? And again, just because the derivative is equal to 0 there does not guarantee a min or a max, but those are the places we're going to want to look for them at least. All right, so example 7, we want to find critical numbers of this function now. All right, so first step, we're going to figure out what is the derivative, and then we want to know where is that derivative either equal to 0 or where is it undefined. Those are the two things we're looking for. How are we going to find our derivative for this function? It's going to be a product. Good. So if we use product rule here, I'm going to let f be x to the 3/5, and our g function is going to be 4 minus x. All right, so what's f prime going to give us? All right, good. So bring down the 3/5. Keep your x, and then if we subtract 1, we're subtracting 5/5 from that. It's going to give us a negative 2/5 as our exponent. All right, and if we find g prime, what's our g prime going to be this time? Just negative 1, right? Because we have a negative in front of the x here. So negative 1 is our g prime value. All right, now product rule again, remember, it's going to be f g prime plus g f prime. So if we start with our f function, we've got x to the 3/5. We're going to multiply that by g prime, which is just a negative 1. And we're going to add, take your g function, 4 minus x, and we're going to multiply that by f prime, which is 3/5 x to the negative 2/5. Any questions up to that point about finding that derivative? Now, just so you know, right, we could have also just distributed the x to the 3/5 to each of our terms in the parentheses first, and then just use power rule on each term to find the derivative. Either way is fine, right? Once we simplify this, we're going to get the same thing regardless. So it's kind of up to you which way you prefer. If you see it as a product rule first, by all means use product rule. If you want to distribute first here and simplify, you can do that too. Okay. Now, if we go through and simplify this derivative now, we've got x to the 3/5 times negative 1. That's just going to be a negative x to the 3/5. And then over here, I'm going to need to distribute this 3/5 x to the negative 2/5 to each one of these terms now. So 4 times 3/5, that's going to give us 12 fifths, x to the negative 2 fifths. And then if we distribute that to the negative x, that's going to give us a minus 3 fifths x. And then x times x to the negative 2 fifths would give us what? Good, x to the 3 fifths. Perfect. Remember, we're adding those exponents. That's a 1 plus a negative 2 fifths, 5 fifths minus 2 fifths is 3 fifths there. All right, now, remember, what we're trying to figure out is where is this derivative equal to 0? Well, let's go ahead and combine like terms. So I do have a negative x to the 3 fifths and a negative 3 fifths x to the 3 fifths here. We put those together, what's that going to give us? Good, so we get a negative 8 fifths, because negative 1 minus 3 fifths, that's negative 5 fifths minus 3 fifths, negative 8 fifths, and then x to the 3 fifths plus 12 fifths x to the negative 2 fifths. All right, now that we've done that, right, that's as simple as we can get it, really. We're going to move our negative exponent in just a minute. What could we do now if we want to be able to set this equal to 0 and solve for x? So think about, in general, if you have something that looks like this, where you have multiple x's in an expression, and you want to be able to set it equal to 0, what might you do? So tell me if we had something like this. If we had 3x to the third plus 2x squared minus x. And I wanted to set that equal to 0 and solve. What would I do first? Factor, right? We're going to do the same thing here, right? So you would look for any common factors. You would factor those out, because if we can get it in factors, then we can set each factor equal to 0 and we can solve for x. Well, what would be our common factor in this case between those two terms? What's something they have in common, even if you don't know everything they have in common? Okay, so they have some x's in common, right? Now, whenever we factor out an x in general, how do we know how many x's we're going to factor out? What do you look at? Okay, you look at the exponents, right? And then which exponent do you end up factoring out? The lowest, right? So like in the other one where it was x cubed, x squared, and x, you'd factor out the x to the first because it's the lowest exponent. What's our lowest exponent this time? Good, the negative 2 fifths, right? So that's the value I'm going to factor out here. I'm going to factor out an x to the negative 2 fifths. Now let's look at the coefficients, right? We have a negative 8 fifths and a 12 fifths. What's something else I could factor out here then? Good, right? We could factor out 4/5, right? We definitely have the 5 in the denominator. That can come out. And then looking at your numerators here, we have a 4 in common between the 8 and the 12. So I'm going to factor out 4/5. Now let's see what's left over. I factor out 4/5 x to the negative 2/5 from that first term. What are we going to be left with? Okay, so we get a negative 2. And then x to the 5/5, which would just be x to the what power then? First, right? Okay, so in this case, we're just going to get a negative 2x for that first term. Plus, if we factor out 4/5 x to the negative 2/5 from the second term, what are we left with? Just 3, right? Because I'm going to need a 3 there to give us the 12/5. We've already factored out x to the negative 2/5, so that goes away altogether. So that's all that's left over there. Any questions on that part? And if you don't see the fraction factors out, at least try to pull out the 1/5, right? The denominator there, because it makes the next step a little easier. But if you don't see the 4, that's fine, right? It's not going to change anything about our answer. But you always want to factor out the x with the lowest exponent. So that's why we're factoring out x to the negative 2/5 here. Now, what can we do with negative exponents? Move it to the denominator. Good. Because it's being multiplied at this point, right, all of this can go in a single fraction, and I can just move that x to the negative 2/5 to our denominator. 5's already down there. I'm going to get a 5x to the positive 2/5 in our denominator. And then up top, we're going to have the 4, and then the negative 2x plus 3. So again, 5's already down there. Keep it in the denominator. Move the x to the negative 2/5 down there and make it a positive exponent. The 4 is already up top, and the negative 2x plus 3 is also, so keep those in the numerator. All right, now, once we've got it to this point, right, we've got it factored, we've gotten rid of all of our negative exponents, what are we going to do with our derivative at this point? Good. This is where we're going to actually set it equal to 0, but we also have to consider not only where it's equal to 0, but also what? So if we're looking for critical numbers, we're looking for where it's the equal to 0 and where it's what? So either f prime of c is equal to 0 or f prime of c doesn't exist, right? So we've got to figure out where it's equal to 0 and where it's undefined. Those are the two things we're looking for now. Well, how are we going to figure out where it's equal to 0? What would you start with? Good. Set the numerator equal to 0 because that's where the fraction is going to be equal to 0. Notice here the 4 doesn't matter because 4 is never going to be equal to 0. So I can just take the negative 2x plus 3, that factor, set it equal to 0. Now, if I want to know where it's undefined, where the derivative does not exist, what would I do? Well, that's going to be where it's equal to 0, right? What would I have to set up if I want to know where the derivative does not exist now? What would I look at? Whenever the denominator is equal to 0, we know that fraction is not going to have a value, right? Because it's going to be undefined. So I'm going to take the denominator now, 5x to the 2/5, and I'm going to set that equal to 0. So again, we're looking for where's the derivative equal to 0, set the numerator equal to 0, and if you have a fraction, wherever that denominator is equal to 0, that's going to be where it's undefined. That's where the derivative is not going to exist. Now let's solve, right? So if we solve the first one here, what's that going to give us as our x value? So negative 2x plus 3 equals 0 would give us what? Good. So move the 3 over, divide by the negative 2. It's going to give us x equals positive 3/2. And over here now, if we solve this one, what's our x value going to be? What would be your first step? Let's go that way. We'll solve it. What would you do first? Divide by the 5, right? So that's going to give us x to the 2/5. 0 divided by 5 is still 0. And then how would you get x by itself at that point? Okay, so think about it this way. What could I do to both sides if I want to end up with x to the first power? So right now I've got x to the 2/5. I need to end up with x to the first power. What would I have to do to both sides? Okay, so you could technically think of it as the fifth root of x squared, right? Okay, so you could rate it good. That's going to be the easiest way is to raise it to the 5/2 power just to cancel out the 2/5 altogether, right? So if you want to do it step by step, you could do that. Really, if you just raise it to the reciprocal power on both sides, now 2/5 and 5/2, when you multiply those exponents together, those are going to cancel and give us a 1. And over here, 0 to the 5/2, still just 0, right? Any questions there now? All right, and we're done, right? Because this one was just asking us to find critical numbers. Okay, so our critical numbers for this one now, we have 3/2 and 0. Now, again, this doesn't tell us where we necessarily have min and max values, right? These are just the critical numbers that we would want to look at more carefully to see if we have anything interesting happening in the graph there. Okay, so I'm going to actually switch over to Desmos now. We'll look at those two values specifically and see what's actually happening on our graph. All right, so we had x to the 3/5. times 4 minus x. That was our original function. Adjust my y values. Okay, so that's our graph now. Okay, so 3/2, that's 1.5, right? So that's actually this point right here. Notice there is actually a local maximum at 3/2. Okay, so that critical number actually does give us a local max. And we'll see later throughout the unit how we can actually find that value algebraically without needing the graph at all. Okay, so we're heading that direction. Right now, we're just looking at the critical numbers. Now, 0 was another critical number. Okay, and notice here at 0, 0, this function does not have a local min or max there, but what ends up happening is it gets so steep that there's actually a vertical tangent line. That's why it shows up as a critical number. Okay, so it is still a critical number, but notice there is no min or max at that point. The only maximum that we actually get from this is the one that's at 3/2. Any questions about critical numbers right now? All right, so let's take our break right here. So it's 11:01 now, so 11:06 we'll get started back up. We'll finish up this section, only a couple more examples to do there, and then we should be able to get into 3.2 today also. Okay, so 11:06. All right. So critical numbers and extrema. Okay, and we kind of looked at this on the graph there. If f has a local max or min value at c, then c is a critical number of f, right? So basically, if there's going to be a local min or max, then there has to be a critical number there. It kind of goes back to Fermat's theorem by saying, if there's a local min or max and the derivative exists, then that derivative is going to be equal to 0, which makes it a critical number now, right? So this is just telling us, if we have a local min or max, then it has to be a critical number. So finding the critical numbers is going to help us to find all the local min and max values. Just know that not all the critical numbers are necessarily min or max values, okay? All right, so we want to find absolute max and min values of this function now. All right, now notice that we're on a specific domain from -1/2 to 4, right? So they're giving us a restricted domain, and our function's a polynomial. If I want to know the absolute max and min values, we're going to think first about where those critical numbers are, because there could be absolute max and min values there. But then we also have to consider the endpoints this time, because remember, we could have an absolute min or max at the endpoints. Let's start with the critical numbers. How would we find our critical numbers for this function? Good. Find the derivative, set the derivative equal to 0. Okay, so I'm going to find my derivative first. What would the derivative of that function give us? Perfect. 3x squared minus 6x, right? So that's just using our power rule to find that derivative. Now, in this case, this is never going to be undefined, right? Because it's still a polynomial. So we only have to worry about where this one's equal to 0 now. So we'll say 0 equals 3x squared minus x. Good. Now we can factor. How are we going to factor this one? Okay, we can definitely take out x. Anything else? And the 3. Good. So factor out a 3x. Should leave us with x minus 2. All right, now that we've got it factored, now we can do what? Good. Set each factor equal to 0. So we have 3x equals 0. We have x minus 2 equals 0. So that's going to give us x equals 0 over here and x equals positive 2 over here. Perfect. Remember, these are the critical numbers now. Not necessarily where we have a min or a max, but we could have min and max values there. Now, remember, the other places we could have min and maxes now are at the endpoints. Okay, so we have to consider those values too. So if I want to know what the actual absolute max and absolute min value of that function is, what do you think we're going to do next? Good. Plug in all of those x values into the original function and see which one actually gives us the absolute highest and which one gives us the absolute lowest. That's going to be our absolute min and max value. So doesn't matter what we start with. I'll start with the critical numbers here. So f of 0. Again, make sure you're plugging into the original function, not the derivative now. So this is going to be 0 cubed minus 3 times 0 squared plus 1, which is 1. Just based off of that, we still don't know anything, right? We've got to check all 4 to figure out which ones give us the absolute highest and lowest values. I'll do my other critical number now. We'll do f of 2. We have 2 cubed minus 3 times 2 squared plus 1. What's that going to give us? Good. That one's going to be -3. Now we have to check the endpoints because we could have absolute max or min values there. So we'll do f of -1/2. We have -1/2 cubed minus 3 times -1/2 squared plus 1. And what do we get if we do that? Okay, so I'm getting something smaller than that. So let's do the work here. So negative 1/2 cubed, that's a negative 1/8. And we have minus 3 times negative 1/2 squared becomes a positive 1/4 plus 1. This is going to give us negative 1/8 minus 3/4 plus 1. And if we find a common denominator between them all, that's going to be 8. So that's negative 1/8 minus 6/8 plus 8/8. Okay. And so if we do that now, that's negative 7/8 plus 8/8. And so that should give us what then? 1/8. Good. All right. So this one actually comes out to 1/8 now. All right. And then if we look at the last endpoint, that's f of 4. And that's just going to be 4 to the third minus 3 times 4 squared plus 1. So what's that going to give us? 17. Perfect. All right. So those are the values we care about, right? So I'm just going to box them just so we know what we're actually looking at here. It's this value, this value, this value, and this value. Okay. Now, of those values, then, where would our absolute maximum be? 17, right? So this one right here, this is our absolute max value. And then what would our absolute min value be? Negative 3, right? So this is the absolute smallest. So we have an absolute min value, okay, of negative 3. So again, just the process in general, find your derivative, set it equal to 0. Also figure out where it's undefined if it happens to be undefined anywhere. Those are going to give you your critical numbers, and then we need to look at those critical numbers in our original function to figure out which ones give us the highest and lowest points, but also remember to check your endpoints if you're on a set domain in this case. Now, again, the nice part about this is you do have access to Desmos. You can actually graph this with the set domain and actually look to make sure that our answers make sense. Let me show you that real quick. Always good to check. All right, so our function here was x cubed minus 3x squared plus 1. We're only looking from negative 1/2 less than or equal to x, less than or equal to 4. So I'm going to zoom out here, just bump up my y-axis. That's high enough. There we go. All right, so absolute lowest point here does occur at one of our critical numbers because there's a turning point there. So negative 3 is the absolute minimum. And then our absolute maximum occurs out here at that endpoint. Okay, and so 17 is the absolute maximum on that interval now. So again, this is what we did before. That's how we found the local and absolute mins and maxes, was just by looking at the graph. Now we have some calculus that we can use to find those absolute min and max values. Notice we haven't said local yet. Okay, we're going in that direction. Once we get to about 3.3, then we'll be able to actually find those by doing some processes algebraically. But for right now, we're only looking at absolutes. Okay. Any questions on that one right now? All right. example 9. So this is the last example from this section that we're going to do. So we want to use a graphing device first to estimate the absolute min and max values of the function. Then we're going to use our calculus to find the exact values and just make sure that they match up to what we got for the approximations, okay? So our function this time is x minus 2 sine of x. We're only looking at the interval from 0 to 2 pi, though. So we're going to start there. We're going to graph this in Desmos. We're going to find the absolute min and max values, which are going to be decimals in this case. That's why they're going to be approximations. Then we're going to look at in part B, how do we find those exact values so that we can get something, either in terms of square roots or pies or something like that, that's not an approximation. All right, so switch over to Desmos first. All right, so this time we've got x minus 2 sine of x. So there's our graph. We're only looking, though, from 0 to 2 pi, so less than or equal to x, less than or equal to 2 pi. Okay, so that's what we care about this time. Now, looking at that graph, where does it look like we have, let's start with minimum, right? So we're looking for an absolute minimum. Approximately, where does it look like that absolute minimum occurs? All right, so the maximum, absolute maximum, I agree, looks like it happens around 5, right? So we go down there. Okay, so that's our point. Now notice Desmos actually does some trig for you. We get the value, right? But in terms of the x value, it actually tells you it's at 5 pi over 3. But the actual value there, the approximation for the absolute max, is 6.968. Okay. Now, where does it look like the absolute minimum goes? Where does it occur? Around 1, right? Okay, so again, we don't know exactly. Okay, this tells us that is actually pi over 3. But again, the absolute minimum value now is going to be negative 0.685. And that's all we were doing with the graph, right? Okay, so Dean said, would it be easier if they were stepping by pi over 2? If you needed to know more specifically where they were, yeah, right? But in this case, we're just trying to find an approximation, a decimal approximation of the min and max value, the absolute min and max value. So it really doesn't matter because we're just going to click on those points anyway and just get those decimals, okay? And Desmos is going to give you the nice pi values for the x's at least, but in terms of the y's, right, it's not going to do radicals, and that's what happens here is these actually come out as radical values, so we're going to look at how we can actually find those using some calculus now. All right, so those are the decimal approximations. Now we want to go back and we want to figure out what the exact values for the min and max are going to be. All right, so what would be our first step here if we want to find the absolute min and max values? Find your derivative. Perfect. If we find the derivative this time, f prime of x is going to give us what? Perfect. 1 minus 2 cosine x. Right? So derivative of x is just 1. Derivative of sine gives us cosine, so that's where the negative 2 cosine x comes from. Now that we have our derivative, what are we going to do next? Set it equal to 0. Perfect. It's never going to be undefined, right? So it's only where it's equal to 0 that we have to worry about. We got 0 equals 1 minus 2 cosine x. What would you do next to solve this now? Okay, we can add the 2 cosine x. So we get 2 cosine x equals 1. Then what? Divide by the 2. So cosine x equals 1/2. And now what? Good. We need to find the inverse cosine of both sides, right? So we're basically saying x is going to be equal to the inverse cosine or arc cosine of 1/2. Well, that means we're looking for the angle where the cosine value is 1/2. Where would that happen? Good. Pi over 3, right? First quadrant is the first place. But also, if we're on the interval here from 0 to 2 pi, cosine would also be positive 1/2 in the fourth quadrant, and so that would be at 5 pi over 3. Perfect. And those are the values we saw on the graph, right? So we saw x values, but this is how you would actually do it algebraically to get to that point where we know the x values. Now that we have those x values, what are we going to do next? Plug it in. Where are we plugging it in? Original function. Good. So we're going to find f of pi over 3. So that's going to give us pi over 3 minus 2 times the sine of pi over 3. So pi over 3 is an exact value, right? So this is just going to be pi over 3 minus 2 times. What's the sine at pi over 3 going to give us? Good. Square root of 3 over 2. And so when we multiply that now, the 2 should cancel out. And so this is going to work out to pi over 3 minus the square root of 3. Now, if you were to put that into your calculator, right, and just do pi over 3 minus square root of 3, notice this is approximately negative 0.685. Okay, so that's the decimal value that we got at the absolute min value. This now, though, is the exact value for that absolute minimum. Okay, now let's find the absolute max. Now we're going to substitute the 5 pi over 3 again into the original function. So we have 5 pi over 3 minus 2 times the sine of 5 pi over 3. Okay, so this time 5 pi over 3 again is exact, so keep that. 2 times, what's the sine at 5 pi over 3 now? It's going to be negative square root of 3 over 2, right? Remember, we're in the fourth quadrant now, so sine should be negative there. This time then, when we multiply, the 2's cancel out, but a double negative becomes a positive. So this actually works out to 5 pi over 3 plus the square root of 3. And again, if you just check that in your calculator, 5 pi over 3 plus the square root of 3, this is going to give us approximately 6.968. And notice that's the same decimal we got for the absolute max, but this is our exact value now. So Desmos is nice to check yourself, right? Because it'll give you those decimal values. But in terms of actually showing work, you're going to have to show the steps if you're asked to find exact values, which is typically what I'm going to ask for on a test. Okay. And same thing with WebAssign on the homework. Unless they say round your answer to so many decimal places, they're looking for an exact value. So make sure that you're doing the calculus to find the exact value here. Any questions on that one now? All right. Like I said, that's the last one we're going to do in that section. Now let's move on to point 2. All right, so 3.2, now we're looking at mean value theorem. Okay, so first we're going to start with Rolle's theorem, which is kind of almost what mean value theorem is. Okay, but mean value theorem is a little more specific than Rolle's theorem. So we're going to let f be a function that satisfies the following 3 hypotheses. Okay, so number 1, f is going to be continuous on the closed interval from a to b. Number 2, f has to be differentiable, meaning we can take the derivative on the open interval from a to b. And f of a has to be equal to f of b in this case, right? So that's where mean value theorem is going to differ a little bit. The other 2 criteria are going to be the same, okay, but in this case for Rolle's theorem, f of a has to be equal to f of b, meaning the starting point and the ending point, those y values have to be the same for your interval. If those 3 things are true, then there is a number c in that interval where f prime of c has to be equal to 0. So we have a continuous function on the closed interval. It's differentiable on the open interval, meaning we can find the derivative everywhere on that interval, and the starting and ending points are the same, then somewhere in between there, f prime of c has to be equal to 0. Now, let's think about how this situation relates to Rolle's theorem. Okay, so we're going to think about throwing a ball directly upward. So I'm going to think about what the graph of that would look like if I were to actually sketch a graph of that situation. Let's say I've got my graph here. All right, so if we're going to graph, this is going to be over time now. And we're going to think of our height of the ball with respect to time. So where would we start in a situation where we're throwing a ball directly upward? Where would we start? Okay, at the origin, right? So if we think of it as, the height is 0 to begin with, right? If you want to start it higher than that, like you're throwing it from a few feet above the ground, whatever, it doesn't really matter in this case, right? Okay, but we're throwing it from a height of 0. Now, what's the shape of this graph going to look like over time if I throw this ball directly up? It's going to be parabolic and it's going to be negative, right? Because it's going to go up, but whatever goes up must come down. And so eventually it's going to come back and we're going to catch it. Okay? So we have our starting height, right, at time t equals 0. We're throwing the ball up, it gets higher, but eventually it's going to start to fall back down, and then we're going to catch it here back at a height of 0. Now, Rolle's theorem tells us that if we have a closed interval from a to b, do we have that here? Yes, right? So here's our a, here's our b. We have defined values at each of those endpoints, right? We know what the height is at each of those. Is this function differentiable on the interval, open interval from a to b? Yes, right? I can find the derivative. It's a nice smooth curve. I can find the derivative at any of the points along that curve now. The last piece here is, are the endpoints equal to each other? So is f of a equal to f of b? Yes, right? So f of a is at 0, f of b is also at 0. Okay, so f of a is equal to f of b. If all 3 of those things are true, Rolle's theorem tells us there has to be a value c in that interval where f prime of c is equal to 0. Do we see that here? Yes, right? Where does that happen? Where derivative be equal to 0? It would be the vertex of that parabola, right? So in this case, it's that highest point, the maximum. If you were to put a tangent line there, we would say that f prime of c is equal to 0 right there. And so this value of c is in that interval. That's where our derivative would be equal to 0. So again, as long as your endpoints are defined, they have the same value, and the function's differentiable and continuous on that interval. There's some value in there where you're going to have a horizontal tangent line, meaning that we're going to have a min or a max, right? So that's what this is going to be useful for now, is if you know all three of those things are true, then we know somewhere in there there's going to be a min or a max value. Any questions on that now? All right. Now we want to prove that this equation has exactly one real root. Now, first thing we have to do to prove this is we have to show that there's at least one real root. Okay, so we need to show first that there's at least one, and then we need to find a way to prove that it's the only one. So think about what we know and what we've looked at previously for showing that there's a root somewhere. Any thoughts on how we could show that there's at least one real root somewhere on that function? All right, so taking the derivative and setting it equal to 0 would give us critical numbers, and those could tell us where we have turning points, right? But that's not necessarily going to show us where it crosses the x-axis, where it has a root. So we actually don't need a derivative here. Any other ideas how we've shown roots in the past? And the derivative will come in later, right? Because that's how we're going to help to show that there's exactly one. For right now, I just need to show there's at least one somewhere. Okay, so think back to when we did intermediate value theorem. And that was one of the questions on the last test. How did we show that there was a root in a certain interval using intermediate value theorem? So what does our intermediate value theorem tell us? Start there. Okay. So we could plug in 0, right? But if we're plugging in 0, what's that going to do for us? Okay. So yeah, and don't worry about the fact that this is equal to 0, right? Just we're thinking of this more as a function at this point, right? So it's really just, if we substitute 0, let me do that just to show you what happens, right? So f0 equals 0 cubed plus 0 minus 1. That is indeed equal to -1, right? So we know the function at 0 is equal to -1. If I want to use intermediate value theorem, though, what else would I need to show? We need to get a positive value for our function, and it has to be continuous. Good, right? So first off, is this function going to be continuous? Yeah, right. It's polynomial. We know for sure that this function is a continuous function. So that's the first criteria for intermediate value theorem. Now we need to show that there's some x value that gives us a negative, some value that gives us a positive, and as long as that's the case, then we know somewhere in between there, it has to pass through 0. Well, do you see an x value that we could plug in here that would give us a positive value instead? 2 works, right? So if we do f of 2, it's going to be 2 to the third plus 2 minus 1. 2 to the third is 8, plus 2 is 10, minus 1 should give us 9. In this case now, because this one is less than 0 and this one is greater than 0, by the intermediate value theorem, we know there's at least one real root on the interval from 0 to 2. Okay. Since those are the 2 x values we chose, we know now that it's going to cross the x-axis somewhere between 0 and 2. Now what we have to show is that's the only place that it crosses the x-axis. Right? Because if we know there's at least 1, if we can show that it never crosses again, we know there's exactly 1. How could we show that this graph is never going to cross again except for that point that's between 0 and 2 now? So let's think about it this way. Let's assume for a minute, here's 2 over here. We know it crosses somewhere in here, right? And it went from negative to positive, so we know it's going up like this. Now, if there's another place where it crosses the x-axis, what would have to happen? What would this function have to do in order to cross somewhere else? Okay, we'd have to have somewhere else where the value flips signs, right? I agree with that. But just in general with this function, we know it's continuous, right? What would have to happen for the value of the function to even flip signs? For this to pass back through. Why would there need to be a critical number? Why would we have to have a critical number in order for this one to pass through the x-axis again? So just think about it this way, right? If I had, let's just say, for instance, there was another point over here or another point over here where it passes through. What would have to happen to that function in order for it to pass through either one of those points? Right? If all I know right now is that it's increasing and going through this point right here. It has to go back down or back up on the other side, right? So it's either got to turn around and go through here, or it's got to turn around and go through here, right? Those are the 2 options. Well, for it to turn around, the derivative has to be equal to 0 because we'd have to have a horizontal tangent there, which means we'd have to have a critical number. So if we can show that there's no critical numbers for this function now, then we know it's never going to change direction and it can't pass back through the x-axis. Okay, so that's our goal now. How could we show that there's no critical numbers? What will we need to do first? Take the derivative, right? So what's our derivative going to be this time? Good. 3x squared plus 1. Okay. Now, if we wanted to find critical numbers, what would you do next? Set it equal to 0. So if we set this equal to 0 now, how would you solve that? Good. Move the 1, so we get negative 1 equals 3x squared. Then divide by your 3, negative 1/3 equals x squared. And then what? Take the square root. So we get the square root of negative 1/3, technically plus or minus. Okay. So what does that tell us? They're imaginary, right? So if we get imaginary values here, do we have any critical numbers? No, right? Because in terms of the graph, all we care about are real values, right? So in this case, there are no critical numbers. And another way to think about that is that 3x squared plus 1 always going to be greater than, or sorry, strictly greater than 0. Okay, it can never be equal to 0 because x squared is always positive. Multiplying that by 3 is always positive. Adding 1 makes it positive, right? Okay, so that's always going to be a positive value. You can't get 0. Therefore, there's no critical numbers to that one. So now we know there's at least one real root on that interval from 0 to 2. We know there's no critical numbers, meaning it never changes direction. Therefore, there's only one real root to that function now. So that's how you would prove that, by showing, first off, there's at least one, and then that's the only one. And the way we show it's the only one is that there's no other turning points on the graph. Okay? Now, obviously, if you go on to, do an advanced math degree or something and take a master's class in advanced calculus, then you would do a lot more documentation here and have a lot more, exact sentences about exactly what's happening. And for our purposes right now, just understanding Rolle's theorem and what part it plays in showing, right, that there are no turning points, that's what I want you to recognize here. Okay, so intermediate value theorem to show there's one root, and at least one root, right? And then using your critical numbers to show there's no more than that because there's no turning points. All right. Now, here's our mean value theorem. Don't let f be a function. Yeah, so Paulina, basically when you get to Calc 3, that's kind of the main calculus stuff. Then there's differential equations, which is still calculus based. There's advanced calculus, which is like a master's level calculus class. Linear algebra really doesn't use calculus. I actually took a statistics class that was calculus based in college, though. So you can actually use calculus for a lot of different math topics. But yeah, linear algebra does come later, right? It's in, you have to take it, after like Calc 2 or whatever. But generally, as long as you've had, your pre-cal and your trig, then you're good for that class. Because there's really no calculus involved in it. But yeah, they're definitely more advanced calculus beyond even what we cover here. Okay. All right. So mean value theorem, we're going to let f be a function that satisfies the following hypotheses. Again, the first two here are exactly the same as what we saw with Rolle's, right? So f has to be continuous on the closed interval. It's got to be differentiable on the open interval. The difference here now is the starting and ending points don't have to be the same. Okay, so that's the one thing that's different between Rolle's theorem and mean value. So then there's going to be a number c in our interval where f prime of c is equal to f of b minus f of a over b minus a. Well, what does this formula right here look like? Okay, we did do a limit with this, right? But what does just f of b minus f of a over b minus a represent? It's a slope, right? So just notice here, right? All we're doing is y minus y over x minus x. That's the slope. So we're just saying now that the derivative at a point C is going to be equal to the slope between A and B. So if you were to calculate the slope between points A and point B, there's going to be some point in between there where the slope of the tangent line is going to be the same as that one. Okay, and you can see that in the picture down here, right? If we go from A to B in that first one, that's the blue line. The slope of that line now, there's going to be some other point where we could draw a tangent line that would have that same slope. Right, and then same thing with the other graph. Now we're just saying there could be multiple points where that happens, right? We know there's at least one. Maybe there could be multiple where the slope between A and B is the same as the slope of the tangent line at some other point on our curve. Okay, so there has to be at least one place where that happens, but there could be multiple. Now, if you think about it, right, this is just a very generalized version of Rolle's theorem, because Rolle's theorem says that if the endpoints are the same, the slope between those 2 points would be 0 because it would be a horizontal line. And so that's how we know there's one point where at least one point where the slope's going to be 0. Now we're saying it doesn't matter where those endpoints are. If we calculate the slope between those endpoints, now we know there's a point on the curve where the derivative's equal to that same slope. Okay. Any questions on mean value theorem? All right, so let's see if we can get through this one. This will be the last one we do today. We want to find the value of C that satisfies mean value theorem for this function on the interval from 0 to 2. All right, so I'm just going to write down the formula for mean value theorem so we can think through it. So this says f prime of C is going to be equal to f of B minus f of A over B minus A. All right, so let's identify what we know first. What's our A value going to be for this one? 0, right? So our interval here gives us the A, and so our B is going to be what? 2. So now I can go ahead and start substituting in here. So I know f prime of C is going to be equal to f of 2 minus f of 0 over 2 minus 0. Well, how can we find f of 2 and f of 0 now? Just plug them in, right? We're given the function, so I'll come over here and do that. F of 2 is just going to be 2 cubed minus 2. And so what would that give us? That one's going to be 6. Good. And then f of 0 would be what? Perfect. So 0 cubed minus 0 is just 0. So now we know that f prime of C is going to be 6 minus 0 over 2 minus 0, or in this case, that's just 6 over 2. So f prime of C should be equal to 3. How can we find the actual C value then where that happens? And for the sake of time, I know we're out of time here, we're going to take the derivative and we're going to set it equal to 3 in this case, right? Since we know that derivative should be equal to 3, I'm going to find my derivative, f prime of x, which is just 3x squared minus 1. And now I'm going to set that equal to 3. So 3 equals 3x squared minus 1. Now we'll solve, move the 1 over. That's going to give us 4 equals 3x squared. Divide by 3, 4/3 equals x squared. And now we can take the square root plus or minus square root of 4/3 equals x. We can take the square root of 4, so that's going to give us a 2 in the numerator, square root of 3 in the denominator. We get plus or minus 2 over square root of 3. So those are the X values now where we would actually have that. Now, because we're in the interval from 0 to 2, we're only going to be in the positives. So in this case, you would only take that positive 2 over square root of 3. Okay. So use intermediate value theorem, or sorry, mean value theorem first to find the slope that you want to be equal to. Find your derivative, set it equal to that slope, and then solve for the X value where that slope would happen. Okay, so this is the point where the slope would be equal to 3. That's going to be the same as the slope between those two endpoints. Okay. All right, so that's where we'll stop for today. We'll come back on Monday, finish up 3.2 and get into 3.3. Like I said, that homework will get pushed back a day to Tuesday since we won't finish it up until then. Don't forget the homework on 2.8 is due by midnight tonight if you haven't finished that already. Don't forget to complete your test by midnight tomorrow night. Let me know if you've got any questions. Have a great weekend, and I will see you on Monday.